Okay, I guess that's most of y'all. So we can go ahead and get started now. Welcome back from spring break, everybody. Let me go over some updates real quick. And for item number 1 of your warm-up, just tell me how your spring break was. I'll be reading those when you turn that stuff in on Friday. Let me go over a few updates for y'all from the College Board. So I posted a link to it in Google Classroom in the first few days over break, just because the information was fresh and I just wanted to get those announcements out there before, or so that you could take it into account for your own planning. But I believe the only AP test that y'all have is AP Human Geography, right?
Yeah.
Yes.
Yep.
Yeah, so just so y'all know, AP Human Geography's test is on Tuesday, May 12th at 1 p.m. Pacific time. And all of the details about the AP tests have been released on the College Board's website. The link to the COVID-19 specific information is on there as well. So be sure that you know your test date, you know the format of the test. The test will either be one 45-minute question or one 25-minute question followed by a 15-minute question. The cases are different for all of the different AP tests, but those are the two types of forms that those tests can take. Also, if you didn't know, the College Board on their official YouTube channel, they've been doing comprehensive reviews for every AP test for all of the people who don't have access to their teachers teaching online through Zoom or whatever. So if you go to YouTube and you type in College Board AP Human Geography, they have a review of every single unit for the entire AP class. So if you really want to guarantee that 4 or that 5, be sure to go on here and look up all of the videos they have, because this stuff is being produced and put out by the College Board. Like, this is their official message of what it is that they're going to put on that AP test. This is probably one of the best things you can do for yourself to get ready for it. And the wild thing is that, like, this stuff is out there, it's official, it's sanctioned by the College Board, and it's only at about 7,000 views. If you're getting ready for AP Human Geography, be sure to go on to YouTube, check out the College Board's official advanced placement channel, and make your way through the review content. I'm sure these people have been given hints about what will truly appear on the AP test this year and are tailoring their videos accordingly.
Sir Robinson, I have a random question. It's gonna sound weird, but how would you know if your cat's hip is dislocated?
Take them to a veterinarian. That is not a question for me. Yeah.
Oh, okay.
And also, if you do not already have a scientific calculator, please get one. I mentioned this before break started, but you need a scientific calculator for the rest of the math that you are going to be doing. Or you can feel free to make the jump straight to graphing calculator in case you don't want to purchase a scientific one. But it doesn't matter so long as the calculator that you are using has the following buttons: sine, cosine, tangent. This kind of graphing calculator is fine, or you can also have a scientific calculator. Usually the brand that people get is Texas Instruments or Casio. Both are fine. They do the exact same thing. Though most of the scientific calculators that you'll find look like this. This is a Casio. This is fine. Again, the whole point here is that it has a sine, a cosine, and a tangent. Or the other, this is probably the most common one that I see, is the TI-30XS. Again, all that I care about is that it has a sine and a cosine and a tangent, because this chapter that we'll be kicking off today is the most important chapter of the book. This is the one chapter where I'm going to give you a skill that you are expected to use in every math class and every science class for the rest of your life. From now on, math teachers and science teachers will expect you to be fundamentally competent in trigonometry, and we'll start walking down that road today. But first, an easy question on similar figures. I have this triangle with a parallel line on the inside of it. Name the similar figures, and then set up some kind of ratio that will allow you to solve for x. You'll notice here that I have a decimal in the right-hand side, which means that it's fine to answer in the form of a decimal. After that, we'll go over the chapter test. And then after we go over the chapter test, I can work out any of the questions from that y'all would like me to. Then we'll get into our new section. We're going to have kind of a big preamble. A little bit today generally about what trigonometry is and why it is so powerful. And then we will get into notes, though you should know that we won't get into the really meaty part of it until section 4. But section 4, we will have a lot of extra practice and drilling on it simply because it is a difficult skill. There is no denying that. Okay, so let's go ahead and go over this item. Number 1, what are the names of our similar triangles?
Triangle DHL is similar to triangle DJK.
Good. And keep in mind that these have to agree as we go around the triangle. So from D to this other angle to the 90-degree angle has to match with D to this other angle to the 90-degree angle. And of course, because these lines are parallel, this gives us corresponding angles. So this is by A, similarity. Now, to set up these ratios and solve for x, I'm going to go ahead and say, well, I got the bottom length of the small triangle. That's just x. I have the bottom length. Oh, sorry. For some reason, my contrast is off today. I think it's because the sun is so bright and like the light from the window is messing up my camera. Anyway, we have the bottom length of the, we have this length on the small triangle. I'm going to take it and I'm going to divide it by that same length on the big triangle. Yeah. And so let's go ahead and do that for the other lengths as well. So for the small triangle, what's this length?
4.
And then for the big triangle, what's this length?
7.
Okay. Now we can go ahead and we can cross multiply. So this will give me 7x is equal to 4x plus, when we multiply in the 4, it gets distributed. So it's 4 times x and 4 times 1.5. What is 4 times 1.5?
6.
Plus 6. I'll subtract 4x from each side. So this gives me 3x is equal to 6, and therefore x is equal to 2. So on that triangle, that little length there is 2, and that big length is going to be 2 plus 1.5, which is 3.5. Are there any questions on this quick, easy warm-up?
No.
No? Okay. Real quick about the last chapter test. Grades were pretty good, so I'm not going to get too into it. But on the chapter 7 test, every question was worth 2 points with no exceptions. So that means that the test was worth 36 points in total because there were 18 questions. So it's 2 times 36. The bonus question was worth an extra 3 points. And I guess all I'll offer is, are there any questions about the questions? Are there any answers that you would like from the test? Anything like that? I'll give you all a few minutes to open it up. It's still in Google Classroom in case you want to pull it up, in case any of those questions were confusing.
Mr. Robinson, I have a question on the do now. Does it also work if you do x over 4 equals x plus 1.5 over 3?
No. That does not work for parallel segments inside of a triangle. For no, that ratio would not give the same answer.
Mr. Robinson, I have a question about the test.
Yes,
What's the answer to number 11?
2.5. You would
Oh,
set up for
okay.
question number 11 a ratio. So this is real quick is 11 from the test. It would have to be 2x minus 4 over x is equal to 6 over 15. And then solving for x would give you 2.5.
Okay, thank you.
Yeah, you're welcome. Are there any other questions out there from the test? Okay. So now we're going to do our introduction to chapter 8. And like I said, this first set of notes are pretty simple. It's actually a vocab word that we've already learned about, but we're going to learn to apply it in a very specific application. But what I want to focus on today is the introduction to the big idea of what chapter 8 is all about. And chapter 8 is all about trigonometry. And what trigonometry is, I think what a good functional definition of the word trigonometry is that trigonometry is the mathematical study of the interrelations inherent in the values of a triangle. And so up through this very moment, there are a few things we can calculate about triangles, right? Not just things that we can determine. So I'm not talking about like the triangle inequality, where there are limitations on the side lengths that a triangle can have. There are some hard and fast things that we can calculate about triangles. Let's go ahead and start off with an inventory of those things. So what are some things that we can calculate about triangles right now?
The third angle, the measure of the third angle.
That is a great one. So the third angle theorem. So the third angle theorem tells us that for any given triangle, and for the most part, we'll be calling our triangles triangle ABC so that this stuff is standard. Angle A plus angle B plus angle C is always equal to 180 degrees. So what the third angle theorem tells us is that based on this, the triangle angle sum theorem, that if I have two of these, angle C must always be equal to 180 minus those other two angles. If I have two of the angles of a triangle, I actually can always get the third one from that. This is a common use this is commonly used in trigonometry because solving for the angles we're going to find is very useful. What are some other things that we can calculate about triangles?
Side lengths.
And what is a method by which we can calculate side lengths? We really only have one technique that'll do that.
The Pythagorean theorem.
By the Pythagorean theorem.
But that can only be applied to right triangles. So
which can only be applied to right triangles. So this only works if angle C is exactly equal to 90 degrees. But yeah, we have a thing called the Pythagorean theorem, which is the name of one of our sections in this chapter, which even though we know it intimately, right? If this is A, this is B, this is C, what relationship is true? What is it?
A squared plus B squared equals C squared.
So this is true if and only if angle C right here is exactly 90 degrees. But so long as I have two of the side lengths of my right triangle, I can use that to always get the third one. The Pythagorean theorem is also part of trigonometry. And in this chapter, not only will we be using it a bunch, but we will also be proving it. We will take two different approaches at showing that this must be true and why it must be true. This is also a commonly used thing in trigonometry. So this is the old stuff. These are two of the tools in our toolbox. Here's the new stuff. In this chapter, we are going to learn that angles can actually be used in order to calculate lengths. And vice versa. The lengths of a triangle can be used to calculate their angles. Here's a really wild example of this. If I told you I had a right triangle that had the following lengths, 3 and 4, what else can you know?
The angle measurements of both other angles and the hypotenuse length.
What you can calculate right now is the fact that the hypotenuse is what?
5.
This hypotenuse is 5. So based on the current information, this side, this angle, and this side, you could know this. Here's the other thing that we're going to figure out how to do this chapter. There's also sufficient information here to calculate the angles. So even though I only know that this one is 90 degrees, here's what I can tell you. This angle down here is 36.87 degrees, and this angle up here is 53.13 degrees. And learning to calculate these two angles is going to be one of the main focuses of our work this chapter. And it's a thing that you need a calculator for, which is why I need you to get a scientific calculator with sine, cosine, and tangent. Is this first part okay? Again, I'm not telling you how I got these. All I'm telling you right now is that it is possible to get the angles from the numbers 3 and 4 and 5. And here is the other major skill that we are going to learn this chapter. We are going to learn that the Pythagorean theorem and trigonometry more broadly, not only does it apply to right triangles, this is just the easiest case where it applies, but Pythagorean theorem and trig also apply equally to oblique triangles. And oblique triangles is just a catch-all for any triangle which is not a right triangle. So the easiest definition of, hey, what is an oblique triangle? An oblique triangle just means not right. So not only will our trigonometry give us exquisite tools with which we can work on right triangles, trigonometry will also give us exquisite tools with which we can work on oblique triangles.
Isn't oblique like a muscle or something?
Yeah, it's also a muscle. It's the muscles on the sides of your abs that like outline your six-pack when you get buff. Yeah. Anyway, so here's just a quick like motivator in terms of why it is that angles and lengths must be inherently related. Y'all see my GeoGebra page here?
Yeah.
Okay. So here's what's going on with this GeoGebra page, right? These sliders affect length. So blue will change the length of AB, green will change the length of AC, and red will change the length of BC. And now notice that if I take them and I close them, it makes a triangle, right? And right now with the triangle in this position, with the side lengths being 9 and 7.6 and 4.2, that is determining the angles, right? This angle is 95, and this angle is 28, and it has to be highly determinative of that angle, because what happens if I change the angle? What happens if I move this out?
It's not a triangle.
It ceases to be a triangle. It no longer closes, right? So all I want to suggest by this is that there is something about the lengths which is determining the angles. Because again, right, this green length can only fall along this circle. The red length can only fall along this other circle. And because of the way that these two circles intersect, if these are the three lengths I have to play with, 9 and 7.6 and 2.3, there is literally one way and one way only that I can close this triangle, and that is by putting red and green at the correct position such that they can line up, and I can, sorry, the green one's off, so that I can make a triangle. So it's fairly intuitive that if lengths are fixed to close the triangle, that chooses the angles. And if angles are fixed the same way around, that will also have a way of choosing the side lengths. However, today we're going to start it off real basic. Today we're going to do a little bit of review. Today we're going to be talking about the geometric mean, which is something we talked about in the first section of last chapter. But in this section, we are going to give a hard and fast reason for it. The geometric mean can be very useful to us in solving for the altitudes of triangles. So today, 8.1, we're just going to talk real quick about the geometric mean. And its relationship to altitudes. Okay. So the reason why this might interest us is the simple fact that at the end of this chapter, we'll be talking once again about oblique triangles, and it's important to appreciate that oblique triangles always contain two or more right triangles. So if I have some messed up set of triangles, if I have some triangle like this, and I'm like, oh, hey, I don't know very much about this triangle, a common diagram that we're going to be drawing a lot is that within this oblique triangle, right, and the reason it's oblique is that none of these angles are equal to 90. So I don't know what they are, but D is not 90 degrees, E is not 90 degrees, and F is not 90 degrees. However, I can always make this into two right triangles by dropping down an altitude. Drop down an altitude. And the definition of an altitude is the same way that an altitude is the height of an airplane from the ground, and that height is measured 90 degrees to the Earth's surface. The thing that makes this an altitude is the fact that it drops down and makes 90 degrees with whatever the bottom side length is. So now, if I really needed to, if I wanted to hit this guy with the Pythagorean theorem, I could do that as long as I define these lengths, because I could have this be A and B, C and D and E, lowercase letters for those side lengths, right? Where the actual outside side lengths for the big triangle would be A plus B, that's this length, E and D here. But now that I have taken this oblique triangle and I've split it up with an altitude, this now allows me to set up two different Pythagorean theorem recipes. I could say A squared plus C squared is equal to E squared. This is just the Pythagorean theorem for the left-hand side triangle. And I could do the same thing for the guy on the right. I could say B squared plus C squared is equal to D squared. And if you got fancy and if you didn't have all of these letters, you could always substitute one of these C squareds for one of these C squareds and end up with an equation which describes the whole triangle. This isn't what this section is about, but we will be coming back to this in a few sections. I just wanted to give it a bit of a shout out right now. Here's what this section is actually about. A right triangle with an altitude makes use of the geometric mean. And let's start off by doing a quick review of geometric mean. So let's just say that I had an arithmetic mean. And a geometric mean. And the numbers that I like to use for this are 4 and 9. Okay. How do I take an arithmetic mean? What does it mean to take a mean?
You add them up and then
You add them up and divide by the number of like measurements.
Yep, yeah, it's the exact same thing as taking an average. So for the taking of an arithmetic mean, we do arithmetic, we do addition, subtraction, multiplication, and division. And I say 4 plus 9, then divided by 2, would give me 13 over 2, which is 7.5 or whatever, right? However, I can also take the geometric mean of 4 and 9, which is another way of finding a number in between 4 and 9. But this number, 13.5, is literally the exact same distance away from 4 that it is from 9. That's what this procedure does. We put 4 and 9 on a number line, and this is finding the midpoint. The exact midpoint in here is 13 over 2. What about the geometric mean? How do I get this mean?
You have to get the square roots of each number and then multiply them together.
It's not that we're taking the square root of each number and multiplying those together. We're multiplying them together and taking the grand square root of the product, which, to be fair, will have the same outcome. So this is to say that I want the square root of 4 times 9. And what is 4 times 9?
36.
So this is actually root 36. And what's the square root of 36?
6.
6. So this is another way of locating a number in between 4 and 9. However, 4, 5, 6, 7, 8, right, is right here and is at the exact same distance from the two numbers that produce it.
Nope.
Nope. It is closer to one side than it is to the other. So my question is, well, what is exactly locating this point? What are we doing? The geometric mean, x, is the number that satisfies the following relationship. And this is the same definition that we gave it earlier. So the geometric mean of A and B, which in that last example, A and B, was just 4 and 9. The geometric mean of A and B is the value of x, which satisfies the following relationship. A over x is equal to x over b. So in that previous question, that is to say that 4 over 6 is equal to 6 over 9. And you will notice that on the right, both of those fractions simplify to the same thing. They both boil down to 2/3. The reason why this works out is that normally here, to solve for x, what would we do? How do we solve a proportion?
Cross multiply.
Multiply.
Cross multiply, so I get that AB is equal to x squared. And then to get x alone, x is going to be equal to the square root of AB.
Yeah.
So
What's
just remember,
ST? What's ST?
Such that.
Oh,
Yeah, it's saying that this is conditional on this definition.
okay.
And here's why we care. The very, very specific case of a right triangle with an altitude. Let's go ahead and start off with a right triangle with an altitude, and I'm going to call it triangle ABC, where our right angle is C, just because that's common and traditional. So here's A and B and C is 90 degrees. And I'm going to drop down my altitude from this 90-degree angle down to a point P, right here. And since CP is an altitude, by definition of it being an altitude, this angle right here is also 90 degrees. What was the last chapter all about?
Similarity.
Last chapter was all about similarity. And in our warm-up, we relied on AA similarity in order to talk about various similar triangles, right? Here's a wild thought. How many similar triangles are we looking at?
3,
How is it 3?
because one
Oh,
to the
there's
left, one to the right, and then one's the whole thing.
Very good. So the gimmick here is that because of this altitude, this is not just producing 2 similar triangles, it's actually producing 3 separate similar triangles, because this triangle, and the big triangle, they all actually have the exact same sets of angles. And by those rules, that allows us to write 3 statements of AA similarity. And so let's go ahead and start off by writing our 3 triangle similarity statement. So I'm going to start off with the big triangle, and I'll call it ABC, just because that seems like a good logical way to write that out. So it's triangle A, then B, then C. And notice I'm ending on my 90-degree angle, right? A to B to C ends with our 90-degree angle. So when we write our other triangles, we are going to also write down the name of the triangle ending in the 90-degree angle. So let's go ahead and line up the big triangle ABC's angles with this little guy here on the side. What angle do you think lines up with angle A for this guy?
A.
A, that's easy. Angle A is congruent to angle A. And this went A, B, C. So I started at angle A, and then I hit the other acute angle, and then I finished on the 90-degree angle. I need to do that same thing, but for this little guy here. So if we're starting at angle A, what's our acute angle?
C.
A to C, and then we finish on our 90-degree angle, P. So these 2 triangles right here, these are similar by AA similarity, yeah? Okay. And then we also get a similarity statement for what's going over here on the right. And how do you think that plays out if we're going to line it up with what's going on here?
then it would be angle BCP.
So here I'm starting with angle A, right?
Yeah.
Which is an acute angle, and then another acute angle, and then we finish on our 90-degree angle. So I want to name out this little triangle over here on the right in the exact same order. So I know that I need to finish on the 90-degree angle. So I know that the last letter of it's going to be P, right?
Yeah.
However, is it fair to say that angle B for this triangle on the right should be congruent to the original triangle's angle B?
Yes.
Is that fair?
Yeah.
So since that's in the middle, that should go in the middle. So what is the first corner over here?
C.
C. So all 3 of these triangles are similar to one another by the AA similarity rules, which allows us to set up a whole bunch of wacky possible ratios. Let me give you one example of a possible ratio and a type of question that you're going to solve a bunch in this section of homework. Let's go ahead and say that this length here, AB, is equal to 25. And this length right here, AC, is equal to 15. So this here is 15. And then this long length from here to here, all of that is 25. So you want to hear something weird?
Sure.
That's actually enough information to solve for every other length on this triangle. So by knowing that this is 15, this here is 25, that's sufficient information to get the other side length and the geometric mean. So I'll call this x, the altitude, and then this side length over here, I'll call that y. So how do we get y?
Pythagorean theorem.
Yeah, and that's kind of a trick question, right? So please keep in mind that just because there's other fancy stuff going on, whenever there's a right triangle, you can always use the Pythagorean theorem to use that to build out information. So we'll actually do that last. However, what I want to do first is let's find a way that we can solve for x. Consider the following proportion that I can build out here. I'm going to build out two separate proportions that both utilize CP, right? This length that I have right here, yeah? And to do that, I'm going to rely on the fact that, well, CP is here, and CP is also here in that second part of the triangle, right? So consider the following proportion. For this guy, I could say that, well, CP, the length made of the last two letters, divided by AP, right, the length of the first and the last letters, would have to be equal to, right, assuming all pieces of this similarity statement are correct. What would this have to be equal to? So CP is the last two letters. What are the last two letters over here?
BP over CP.
BP, the last two letters, divided by the first and the last letter, divided by CP. Is that okay?
Yes.
And this is honestly the punchline of today's lesson. Let's go ahead and solve for CP. So CP squared is going to be equal to AP multiplied by BP. And so CP, the length of our altitude, must be equal to the square root of AP multiplied by BP. So here is the special lesson that we can take away. The altitude within a right triangle can be calculated by geometric mean. And we know that to be true because the similarity statement set up involves the altitude from two different triangles, and it shows that it can fulfill the exact same proportionality that gives us the definition of the geometric mean. However, do we have the two sublengths that will give that back to us? Do we have AP? Do we have PB?
Not yet.
No, but we can solve for it.
But we can solve for it. So here's one thing that we know. What do AP and PB, what do they add up to?
25.
25, yeah.
AP plus PB in total would give us AB. So I know that these two, they have to add up to 25. However, like I said before, there is actually sufficient information to solve for all of these bits and pieces. So just to make it a little bit easier on us, instead of calling it AP and PB, I'm also going to name those with single letters, W and Z.
Is point P the midpoint of that line or no?
No, it is the point that makes the altitude.
Oh, okay.
Yeah. So no, it is not the midpoint. That would be a different type of segment. Instead of being the altitude, it would be the mid segment.
Oh, okay.
Good question. And so in order to get X, I need W and Z. And guess what I have to do in order to get W and Z?
Set up a proportion.
Not yet. We can't do that because to solve for unknown values in a proportion, we need to know at least two of the numbers to start off with. But right now I only know one number. What's a way that I can generate another number? We hinted at it earlier.
Pythagorean.
Pythagorean theorem. Getting y first is actually the easiest thing to do. So let's start off by getting y, and then we'll continue the work on the next page. So here's what I know about y. What is the hypotenuse of this right triangle?
AC.
That is not the hypotenuse of the right triangle. The big triangle, what's the hypotenuse?
AB.
AB. For the big triangle, this is the long side. So to solve for y, we're going to start off with 25 squared is equal to what?
15.
15 squared plus y squared.
Okay. So go ahead, take that, execute, solve for y.
Y is 20.
Y is exactly 20. If you do 25 squared minus 15 squared, that gives us
25 minus
400. And then the square root of 400 gives us back exactly 20. So that's the second piece of our puzzle. I got 15, I got 20, and now we can get W and Z.
Now we could set up a proportion for it.
Yep. And I'm sorry, real quick, just because, oh, wait. Is it still sharing the, okay, yeah. Let me redraw it real quick, just so that it can be along the side here to help us with our thoughts. 15, y is equal to 20, W, Z, X, A, C, B. Okay, so now that we know that y is equal to 20, would y'all like to solve for W or Z first?
Z.
Okay, we'll solve for Z first. So again, just a reminder of our proportionality. Triangle ABC is similar to triangle ACP, is similar to triangle CBP, and understanding how to read this will give us all of our answers, right? Oh, sorry, this is point P. So yeah, right here, we want Z. So that's length PB. Where do we see BP as a segment?
The last one.
DBP.
The last one, right here. So I know that I'm going to want to set up some sort of proportionality with this guy, right? And then the other triangle that I have all the information for, well, that's the big triangle, right? So if I want BP, we're going to compare that to the big triangle. So here's what I'm going to do. I'm going to say that BP, which is Z, divided by something is going to have to be equal to the same proportion, but for this triangle over here. So BP corresponds to BC, BC. And then what should I choose as my other length? What will make this solvable for us?
AC to over W or something? AC and W?
So you want to make it so that when you are solving, you only have one variable to solve for, not multiple. So what I'm going to do is I'm going to look here, and I'm going to look at what segments I have. I want BP. Do I have PC?
No.
I don't. So I'm going to write this proportion with BC because I know what BC is. So I'm going to say C divided by BC. BC, the first two letters, has to correspond to the same thing over here. It's got to correspond to the first two letters. So if this is BP over BC, this has to be BC over AB. And now I can go ahead and I can substitute in my values. How long is BC?
25.
20?
25. Right.
20?
Oh, I couldn't see. My bad.
And then how long is AB?
25.
25, yeah.
And this is going to be equal to Z divided by BC. How long is BC?
20.
20.
20. And now we can cross multiply and solve for Z. Z must be equal to 400 divided by 25, which is equal to 16. Yeah?
I couldn't see the 20.
So that means that right here, Z is equal to 16. And
Yeah.
so that also gives us W, doesn't it?
Yeah,
Because
because you
25
do 25 minus 16.
16.
Yeah, because I know that this total length is 25. And so if Z is 16, W has to be what?
9.
W has to be equal to 9. And now that I have W and I have Z, that gives me all the information I need to solve for the altitude. Because that's what we set up on the previous page. That was the point of all this work. The altitude must be equal to the geometric mean of these two subsegments. So I can say that our altitude X, therefore, X must be equal to the square root of 9 times 16, which is going to be equal to 12.
Wait, why do you do that?
The justification for it was in the previous page. And so if this is 9 and this is 16, this X must be equal to 12. And all of these other calculations, the fact that this is 20, the fact that this segment is 9 individually, the fact that this segment is 16 individually, all of those calculations are based on the fact that this was 15 and this was 25. Nonetheless, that's it for today. So when it comes to right triangles with altitudes, the length of the altitude within that right triangle is the geometric mean of the two subsegments that the altitude leads to. This can be justified using our regular rules that we've been using all last chapter for similar triangles, established by AA similarity. We can set up proportions according to AA similarity and solve. I would be sure to start off any question of this nature by writing down all three of the triangles which are similar to each other. And in the homework, make sure to leave your answer as a square root. So if you get square root of 3, that's the answer, not 1.7 da 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 da. There's only one page of homework and most of the questions on it are going to be very similar. The first half is just asking you to calculate geometric means by this definition. And then the second half is going to ask you to calculate geometric means in fashions very similar to this. Tomorrow, our warm-up question will be the same. And then we'll have that whole period to work on the homework. Any questions on that stuff?
No.
No? Okay. Y'all have a nice day, and I'll see y'all tomorrow at the same time. Welcome back.
You too. Bye, Mr. Robinson.
Peace.
Bye.
See you. Bye.
Bye.